Hi and welcome to Module 4.3 of Digital Signal Processing. In this module we will look at the DFT in practice by showing some analysis example, by showing you how to label the DFT axis to relate the DFT to physical quantities like real-world frequency. We will talk about DFT synthesis, how we move from the frequency domain to the time domain. And finally we will introduce a close relative of the DFT called the discrete Fourier series, which is just a different flavor of DFT applied to periodic signals. You remember that we tried to whet your appetite with respect to Fourier analysis in the beginning of Module 4.1 by showing you a mystery signal, and by showing you that by changing the basis in which the signal is represented, we all of a sudden could see some structure in the data. So now we can go back to that example and analyze it applying what we know about DFT. So we take the DFT of the mystery signal, we plot the real and imaginary part of the DFT, and we see that the structure that appears is a couple of spikes at symmetric positions in the spectrum. Now we already know that this indicates the presence of a strong sinusoidal component, and more importantly, a sinusoidal component that has a frequency which is a multiple of the basic frequency for the space that the signal lives in. Now if you look in detail at what happens in the spectrum, we see that the peaks are for k equal to 64 and for k equal to 960. We also see that the peaks appear only in the real part of the spectrum, and we remember that when this happens, the underlying sinusoid, the sinusoid represented by these peaks, is a cosine. So from this simple visual inspection, we can already write our signal as such. There will be a cosine component, and we will have to determine both the frequency and the initial phase of this cosine. And there will be another part that we can probably call a noise component, in the sense that it doesn't have any structure. Since the imaginary part of the Fourier transform doesn't exhibit any particular peak, we can assume that the phase of the cosine is 0. And as far as the frequency is concerned, we know that the peak occurs at k equals 64. We are in a space of 1024 points, and therefore omega will be equal to 2 pi over 1024, the basic frequency for the space, times 64. If we plot the two components separately at this point, we see that we have indeed a cosine that oscillates 64 times in 1024 points, and we have an additional noise component that doesn't really seem to have any structure. Let's now look at another signal, one that we showed in the introduction to this class, and that is a time series that maps the solar activity since the 1700s. Astronomers have noticed that solar activity could be related to what they call a sunspot number. The details are not really important, but fundamentally a measure of how many solar spots are at any given point in time on the face of the sun. So we have a data set that goes from 1749 to 2003. That is equivalent to 2900 months. Solar spots are computed every month. And as we plot this data, we see that there is an oscillatory behavior. We are interested in finding out if there's any fundamental periodicity in solar activity, so we can take the Fourier transform. The sunspot time series is a real signal. Now, if we're interested just in the magnitude of the DFT coefficients, you remember we need only show the first half of them. Even so, if you look at the first 1500 coefficients, you see that after the 100th coefficient or so, their magnitude becomes too small to be relevant. So in this plot, for clarity, we just show the first 100 DFT coefficients in magnitude. And indeed, we can see that there is not just one peak, but a series of peaks. Now, what is the fundamental period? What is the most dominant mode of this time series? The main peak happens at k equal 22. This tells us that there are 22 cycles over the 2904 data points that we showed in the previous picture. Therefore, the main period of the signal is 2904 over 22, which corresponds to approximately 11 years, which means that solar spot activity has an inherent periodicity of 11 years. We can perform the same analysis with a data set that records the daily temperature over a total of 2920 days. if we take the DFT of this time series, we see that there is actually a very pronounced periodicity in the spectrum. There is basically just one peak. And if we plot the normalized DFT coefficients, so if we divide the DFT coefficients by the length of the temperature vector, we can actually extract some information about the temperature values in this time series. So remember, for instance, the DFT coefficient for k equal to 0 is the non-normalized average of all the data points, because x of 0 is simply the sum of all the points in the time series for n that goes from 0 to big N minus 1. So if we plot the normalized coefficients, the coefficient in 0 will be the average temperature for the time series, which in this case happened to be 12.3 Celsius degrees. And then we remark that there is a peak in the DFT for k equal to 8. So if we sum up what we learned from the DFT about the temperature signal, we know that the average value of the temperature is the 0th DFT coefficient normalized, so 12.3 degrees Celsius. The main peak is at k equal to 8 for a value of 6.4 degrees. What that means is there are 8 cycles of the temperature signal over the entire duration of our data set, which is 2920 days. And so the period is 2900 divided by 8, which happens to be 365 days. So indeed the temperature has a yearly periodicity, as we all know very well. Now the value of the DFT main peak is 6.4 degrees Celsius. Now if we have a sinusoid of the form A cosine of omega n, and we take the DFT of this signal, we will have a peak in magnitude for some index k that has a value of A over 2. Remember the definition of the DFT of a cosine function. So from this we can say that the temperature excursion around the average is twice the value of the DFT main peak, and so we can say that the yearly temperature at the point of measurement for the year was an average of 12.3 degrees plus or minus 12.8. So this is the second example in which, in order to find the real-world frequency of a certain DFT component, we take the total length of the signal and we divide by the location of the peak. This is actually a general method to label the frequency axis of a DFT plot, and it will be very useful in the future when we start analyzing generic signals that have been sampled in a variety of contexts. So if you remember, in Module 2.2, we informally introduced the notion of a clock for a digital signal processing system, and this is really equivalent to associating a certain time interval Ts measured in actual physical seconds between successive samples in a signal. So for instance, for the solar spot signal we had a Ts of 1 month, whereas in the temperature signal the Ts was equal to 1 day. We will see that for audio signal Ts becomes very small because we will need to take at least 8,000 samples per second. Now if we have a value for Ts, which is determined by the experimental setup, we can reason like so. The fastest positive frequency in a digital signal is omega equal to pi. So a sinusoid at that frequency needs 2 samples to do a full revolution. Remember the unit circle. Something that moves at a speed of pi will be here at instant n, here at n plus 1, here at n plus 2. So 2 samples to complete the full revolution. Now the clock Ts can also be expressed as 1 over Fs, where Fs is the frequency of the system. This is a standard relationship between period and frequency for any system. So if the real-world period for the fastest sinusoid in a digital system is 2 times Ts, measured in seconds, the real-world frequency for the fastest sinusoid is Fs over 2. So the maximum frequency, once we've fixed the period between samples, is Fs over 2, or equivalently 1 over 2 Ts. So let's take a concrete example. Suppose I give you an audio file that records a train whistle, and I'm asking you to find out which notes make up the whistle. And of course your idea is to take the DFT of this file and find out the peaks in the Fourier transform, which will probably correspond to the fundamental frequencies of the notes that are being played. So in order to do so, you need some extra information, and namely you need to know the sampling frequency of this file, namely the time between successive samples. So the sampling frequency is fs equal to 8,000 Hertz, which means that ts is 1 over 8,000 seconds. This is the time between samples. And also, the file contains 32,768 samples. We will see later why we often choose signal lengths that are a power of 2. So if you take the DFT of this file and plot its magnitude, you see that there are 3 peaks that probably corresponds to the 3 notes being played. Now, in order to label the axis, remember what we said. The highest frequency for a digital system corresponds to half the inherent sampling rate. And on the DFT vector, this point will correspond to the midpoint in the vector, namely the point for k is equal to n over 2. So here indeed we have the midpoint of the DFT vector, and therefore this will correspond to a frequency of 4 kHz. We also have 3 peaks that take place for different values of k. To find the real frequency there, we just apply a linear mapping from 0 to 4 kHz, and so the frequency of any intermediate point will be 4 kHz divided by the total number of points multiplied by the index k. With this rule, we can find the value in hertz corresponding to the 3 peaks in the DFT, and the values are shown here in the figure. And if you look up the closest note in the Western tuning that these frequencies correspond to, you obtain that the train whistle is nothing but a simple B minor chord. Okay, so far we have looked at DFT as an analysis tool. Let's now spend some time thinking about the synthesis properties of the DFT, how we build the signal starting from DFT coefficients. And to better understand how the DFT reconstruction formula works, it's useful to look at the standard sinusoidal generator that works at one of the standard frequencies in the Fourier basis. So here you have a complex exponential with a frequency which is a multiple of 2 pi over big N and with an initial phase 5k. The way this generator works is by successively generating points on the unit circle starting at the phase 5k and proceeding in increments of 2 pi over big N. We can draw this concisely with this notation, where here inside you have the index of the Fourier frequency that the generator will produce, and the input parameters for the generators are, of course, the initial phase here, and a gain factor a of k that will lead to a of k times to e to the j 2 pi over big N kn plus phi k. So the DFT reconstruction formula can be drawn graphically like a machine composed of big N sinusoidal generators, each one of which will be initialized with a gain factor and with a phase factor. All their outputs will be summed together, and this will give us back the original signal. How do we initialize each one of these blocks? Well, the amplitude will be the amplitude of the corresponding Fourier analysis coefficient, normalized by big N, and the phase will be the phase of the corresponding Fourier analysis coefficient. So let's look at an example. Let's take a simple signal, a 7-point long signal that looks like a triangle, and we perform a Fourier analysis on this vector, and we get 7 Fourier coefficients that we list here in terms of amplitude and phase. Now we initialize the 7 generators with the A's and the Phi's that we found in the analysis part, and then we turn the crank 7 times, and we will sum the outputs together to obtain the original signal. So here is how it works. In the first line, we will show the output of each generator in turn, starting for k equal to 0 up to k equal to 6. And here on the bottom line, we will show the cumulative sum of the outputs as k proceeds from 0 to 6. So the first generator is the one for k equal to 0, so the frequency is 0, and the output will be simply a constant. As a matter of fact, the value of this constant will be equal to a of 0. And so the cumulative sum now has only one term, so the output at this point will look like a constant. For k equal to 1, we have now a sinusoid that will have a certain initial phase and a certain amplitude. And we can see that as we add this to the previous constant, here in gray you see the previous sum, and here the updated sum for k equal to 1, the real part of the signal starts to look a little bit like a triangle. We also have a significant non-negligible imaginary part which will have to disappear in the end because remember we started from a real signal. So as we proceed for k equal to 2, we see that the coefficient amplitude is very small, and so this will be just small adjustments in the sum. It's very hard to see the difference between this step and the previous step. K equal to 3 is very similar, small adjustments. For k equal to 4, we're going in the counterclockwise part of the spectrum, so more adjustments still that will start to bring down the imaginary part to 0. Here you see another small adjustment, and finally k equal to 6, the last coefficient, will completely kill the imaginary part and give us back exactly the signal we were starting from. So why do we think about the DFT reconstruction formula as a machine? Because in reality these machines were used in the past, for instance, to predict the tides. The tide is a periodic phenomenon, and once you find the modes, you can actually use the experimental data to predict the evolution of the tide as a superposition of sinusoidal components. So this machine that was originally invented by Lord Kelvin is nothing but a mechanical implementation of the DFT reconstruction machine that we just saw before. So here's a question. What happens if you turn the crank of the machine more than big N times? Well, it turns out that the output will become periodic. In other words, x of small n plus big N will be equal to x of n. This is actually quite apparent from the structure of the synthesis and analysis formulas of the DFT. Let's start from the synthesis formula. So in theory, the output index small n should go from 0 to big N minus 1. But you can see that it only appears here inside this complex exponential. Now this guy is 2 pi periodic, so if you push n over big N minus 1, this will simply cycle over once again as if n was looping over the 0 to n minus 1 range. So in the end, you can actually safely take n to be from the set of integers, and the output will be an n periodic signal in the time domain. Actually, the same holds for the analysis formula. You can let the index k roam over the entire set of integers, and since it appears only in this complex exponential here, again, it will be as if k was looping over the 0 to n minus 1 range. So what happens really is that you can consider the sequence of DFT coefficients as an n-periodic signal in the frequency domain. Now, when we talk explicitly about the periodicity of the Fourier transform, we prefer to use the term discrete Fourier series, or DFS for short. So the DFS is just a DFT with the periodicity explicit. The DFS maps an n-periodic signal onto an n-periodic sequence of Fourier coefficients. And the inverse DFS maps an n-periodic sequence of Fourier coefficients onto an n-periodic signal. But mathematically the two are the same. It's just a conceptual difference. However, DFS helps us understand, for instance, why we said that the natural shift for finite length sequences is actually a periodic shift. Let's consider an n-periodic sequence x tilde of n. For periodic sequences, shifts are well defined. We can take x tilde of n minus big M, and it's just a normal shift of an infinite two-sided sequence. If we take the DFS of this periodic sequence with a shift, we can work out very easily that the DFT coefficient for index k is equal to the DFT coefficient for index k of the original sequence without the shift. So x of k is simply the DFS of tilde x of n with a phase shift term e to the minus j 2 pi over n big M times k. Similarly, it's very easy to verify that the inverse discrete Fourier series of a vector of DFS coefficients multiplied by a phase delay factor is simply the periodic sequence delayed by m. So this term, e to the minus j 2 pi over n mk, is a delay factor in the frequency domain. So what happens for finite length signals? We saw that in this case a shift is not a well-defined operation, and we need to embed the signal into an infinite length signal either by building a finite support or a periodic signal. Now we can always build x tilde of n as x of n modulus big N. Now mathematically the DFS of this periodic signal is equal to the DFT of the original signal. So the inverse DFT of the DFT of the signal times this delay factor that we showed in the previous slide is numerically equal to the inverse DFS of the same quantity. But we know that the inverse DFS of this will be a delayed periodic sequence. And if we go back to the definition of how we build this periodic sequence, this will be simply x of n minus big N modulus big N. What we have shown here is that if we think of the Fourier representation of a finite length signal, circular shifts are the natural extension of the shift operator to finite length signals because the underlying Fourier representation is the same as that we would use for a periodic signal built on the finite length signal.